in this lecture, we want to talk about properties of a vector space. So there's plenty of properties out there that you're very familiar with in R to the 3 and R to the 4 that are not part of the axioms of a vector space and that would you want to take for granted. So let's see what is there in the following theorem which we're about to prove. Let's look at part number 4 here. If you take any real number and you take the 0 of the vector space, so in R3 that would be 0, 0, 0, well then lambda times 0 should give you 0 back. Okay, and so the problem is that in a general vector space, this is not part of the axioms. And so hence we cannot take this as given and we have to derive this just using the axioms. And so this is a very important part of linear algebra, or on how to to learn and how to write a proof, is that when you're proving something, you cannot just take your intuition as your backup. You really can only take your definitions and results you already have proven. So here, for now, the only thing we know are the axioms of the vector space. So these 8 given properties, and all other properties that we would like to hold, for example, that lambda times 0 gives you back 0, have to be proven just using those axioms. And so that's what we want to do in this theorem. So now in this theorem, we want to prove those following 7 statements. We will just use the axioms, and then afterwards we can take these statements as granted and we can use them henceforward. So the first thing we want to do is a so-called cancellation law, and it states the following, that if you take 3 vectors and you add to a given vector u some vector w, and you add this vector w to another vector v, well then you can cancel this w just like in R, and you get that u is equal to v. Again, it's something that out of your intuition you would think is true and you would probably want to use, but it's not given beforehand. So it needs to be proven. Okay, so as a proof, good proof writing, we always state what we want to show. So we want to show that u is equal to v. And the easiest way of doing this is, well, let's start with u on the left-hand side, and we want to keep on writing equal signs just using axioms and end up with v on the right-hand side. So what can we do? Well, if we start with u, we can use axiom 3. Axiom 3 said, well, you can always add 0 to any given vector and it remains the same. Okay. Well, then, now we're going to use axiom 4. And we're going to use it in the following way, that there is w prime in v such that if I add this w prime to the given w, it gives me back 0. So if I add that, it's the additive invert of w. So here I can remove this 0, or replace the 0 by w plus w prime. Okay. Now we want to move the brackets. Never forget to use axiom 2 and mark it. So we want to move the brackets to the in the front. It's going to be u plus w prime. Great. And we're going to use now the assumption. What does the assumption state? The assumption states that here u plus w, which is what I found here, is actually equal to v times w. So this whole expression I can replace by v plus w. So it's going to be v plus w prime. Then I'm going to use axiom 2 again. So I'm going to move the brackets to the right-hand side. And then I can use axiom 4 again. And the same time as before, that this w prime is the additive inverse to w, so we get here v plus 0. And then, well, I can use axiom 3 again, and I get v. So overall, I get what I wanted, u is equal to v. So see how over every equal sign, I tell the reader what I'm about to do and what I'm using. Yeah, and so this is important when you want to show some property of a vector space just using the axioms, that every time you do a modification, you tell the reader what is the axiom or statement that you're using. So now let's go to part number 2. So here, what does it say? It says that if you have this vector 0 from axiom 3, that this vector is unique. Yeah, axiom 3 just tells you there is a certain 0 element such that when you add this to any vector v, it gives you the vector v back. But it doesn't necessarily say that there could only be one. And what we want to show now is that this vector is unique, meaning there's only one such element. How can we do that? So to show that 0 in v is unique, we pick a second one with the same property. So we let 0 prime in v be such that v plus 0 prime is equal to v for all vectors v and v. And we're going to mark this with star. Okay, so this statement here is going to be marked as star. Okay, and so now we want to show that in this case, the 0 prime is actually equal to the 0 we started with. Okay, great. And the approach is very similar to part 1. We're going to start with 0 in one side of the equation, and we're going to want to end up with 0 prime on the other side of the equation. So first thing we can do is we can use this star property up here. Yeah. So this will tell you that 0 prime acts like 0. So in particular, 0 is equal to 0 prime. Well, and now I want to use that 0 acts like the 0. But if you go back to the axioms, axiom 3 only works from the right-hand side. And so we always have to use axiom 1 again. So axiom 1 says we can flip them, that is equal to 0 prime plus 0. And then we can actually use axiom 3 from the vector space that gets us equal to 0 prime. Yeah, so then here we can conclude actually 0 is equal to 0 prime. So 0 is unique. Great. Let's go to part 3. Let's go back to the statement, and I have it here so that I don't have to scroll up and down. So part 2 said the 0 is unique, and part 3 will tell you that the additive inverse is unique. So that there's only one element for every element v, which we denote by minus v, with the property that v plus this minus v is equal to 0. So the start is the same way as for part 2. We wish to show that minus v is unique. So suppose there is w in v such that v plus w is equal to 0 and v plus minus v is equal to 0 by assumption. Okay, so we have two elements, w and minus v, such that I added up to v becomes 0, and we want to show that these are equal. We need to show that w is equal to minus v. Great. So let us start here. What can we see? Let's look, if I add them up the other way, w plus v, I know by axiom 1, this is going to be v plus w. Then now by assumption, by assumption I mean this red part here. This is equal to 0. Then also by assumption, and here I mean the blue part, so that minus v acts like the additive inverse. That is equal to v plus minus v. And now let's use axiom 1 again to flip them around. And you will see why this helps us now. What I said before is that we can only use things that are given, meaning here the axioms of the vector space. But what we can also use now in part 3 is things we've proven before. So for example, we can use here the cancellation law. Yeah, so in part 3, we already proven part 1. So part 1 we have handy. And you can see here that this is precisely a situation where we can use the cancellation law. We have an element on the left and the same element on the right, so we can cancel the v. Hence, by cancellation law, we obtain what we want, and this is that w is equal to minus v. So this ends the proof of part 3. Now let's go to part 4. Let's see what it says. Part 4 says that if I have a lambda and I take the 0 element and I multiply 0 times the lambda, any real number, I get back the 0 element. As said before, we always want to say what we want to do. So we wish to show that lambda times 0 is equal to 0. And it might seem a little bit dropping from the sky how we start. And I will say something to that a little later. So let us look at the following computations. So I'm going to take this 0 times lambda times 0 twice. First thing I'm going to do is I'm going to use axiom 7 to factorize by lambda. So this is the same as lambda times the sum of 0 plus 0. Then this is axiom 3. I'm going to apply axiom 3 to this term inside here, so I can cancel one of the zeros, and one of the zeros the right hand side. So this is going to be equal to lambda times 0. Now I'm going to use axiom 3 again, but to the outside equation. So what I can do is here I can add 0 by axiom 3. So I have here lambda times 0 plus 0. And now I want to put it to the front, so using axiom 1, so I get 0 plus lambda times 0. And what can we see now? Well, again, we can use cancellation law, cancel the right-hand term, and we get exactly what we want. So by cancellation law, we obtain that 0 times lambda is equal to 0. Let me just mark this. Yeah, so this is what has cancellation law do. Yeah, and so let's go back to what I said at the beginning. Yeah, one might ask, why do we start with this? Yeah, how would they ever come up with this proof? But the point is here that the way we present a proof is not always the way we come up, the same way we come up with the proof. When you present a proof, you want to make it as short and as comprehensible as possible, and you don't really write it necessarily down in the exact sequence or this exact way that you came up with it. So probably what you did is more you started with the middle and you kind of ended up here and then you went to this way or something like that. So you kind of play around with the two things you have here, and you want to get from one to the other. So now let's go to part 5. Part 5 said that if I have a vector and I multiply it times the 0, and this is important here. Now this 0 is a 0 in R, then I get a 0 in V. Yeah. So let me write it with subscripts. So we want to show that 0 in R, scalar multiple times some vector V, is equal to the 0 in V. Yeah, so sometimes when I want to make sure that we know what we're talking about, I do add the subscripts. And here subscript V means that this is the 0 of the vector space, and subscript R means that this is the 0 in R. And if you want to go back up, for example, in part 4, those zeros were all zeros in V. So if you wanted to add the subscript, you would have put all V's here. Okay. And so this becomes very similar to part 4. So we have here 0 V plus 0 V. Let me just look up what is the axiom I want to use. Here I'm going to use axiom 8. So I factor via this V here. And again, these are zeros in R. Okay, great. So we're going to get 0 in R plus 0 in R times the vector V. Then, and now we have to be careful. We might want to say now axiom 3, but axiom 3 just says something about the 0 in the vector space. It doesn't say something about the 0 in R. And here we just say, well, this is addition in R. So you can't take for granted what you know in R. Yeah, so a 0 in R, how does it act? Well, 0 plus 0 becomes just a 0 in R. Okay. So this becomes 0 times V. And now we're going to use axiom 3 because we're going to do similar as above. Add the 0 in V. And then we use axiom 1 again to flip them around. And as above, we use cancellation law to obtain what we want. So now let's talk about part 6. What is it? Okay. Here we're saying the following. If we multiply a vector V times -1, we're going to get the additive inverse of the vector itself. Before I go into the details of the proof, I want to say something more about it. So let V be in V. Okay. Well, then by -V, we denote the unique additive inverse of V. That means the element in V such that V plus -V is equal to 0. And then a lot of attention you have to show here to not go back to your usual intuition, yeah? So for example, this here is not equal to V minus V. In particular, this makes no sense. I really want to emphasize this here, yeah? There's no subtraction defined in a vector space. Yeah, so no minus. Yeah, only addition. So every time you want to write something like V plus and then the unique additive inverse, yeah? So really this here, this minus should not be seen as an operation, or at least not as an operation where it's a binary operation. You should really think of this as the name of the unique additive inverse of V. So minus V is as much a vector as V. Yeah? And so this here, this plus, this minus here cannot be replaced by a subtraction sign. If you do have more questions about that, please do ask in a live lecture, and I'm more than happy to talk a little bit more about it, because it is a difficult detail to kind of wrap your head around it if you've been using the subtraction symbol for so many years. Okay, but without actually understanding this, I think it might be difficult to see why is there even anything that you need to prove for part 6 in this note. Okay, and what we can use here now, so we are going on to proving it, is that this guy here is the unique additive inverse. So in order to show that minus 1 times v is equal to minus v, it's enough to show that it behaves the same way. So it is enough to show that v plus minus 1v, yeah, so this is another element, maybe I want to put even more brackets here, is equal to 0 by uniqueness of minus v. Yeah, let me repeat. If this guy adding to v becomes 0, and since this here is the unique one that does this, then these two have to be the same. Okay, so let us compute. So we're going to start with this element here. Now, by axiom 5, we can put a 1 in front of the v. So this is the same as this. Then now by axiom 8, we can factor via v. So get here 1 plus minus 1 times v. Then these ones here are in R, so we can use addition in R. And remember, as before, in R, we are allowed to use all of our knowledge. So 1 plus minus 1, what is it? It's the 0 in R. Oh, and then, yeah, we don't have that 0 times v is equal to 0 in the vector space by the axioms, but we've just shown it. So again, we can always use things we've already shown. So by part 5, this is actually equal to 0. And by 0, I mean the 0 in v. And this is the end of the proof of part 6. And so now we are left with proving part 7. What is 7 saying? Okay, it says a whole bunch of equalities, and you can think of 7 as the generalization of part 6. So part 6 is just talking about the minus 1, and here we're going on and talking about the all scalars. Yeah. So what is this? This is the unique additive inverse of lambda times v. So you look at lambda v as a vector, and this minus tells you get the unique additive inverse. This is the same as, well, multiplying the vector times minus lambda. And so this minus here is minus in R. Yeah? And this is also equal to, well, multiplying the unique additive inverse of v times lambda. Yeah, so again, it's very important to understand the difference in the minus. Yeah, so this minus and this minus are the same. They tell you it's the unique additive inverse, where this minus is a minus in R. Yeah? So the difference is the same as for 0. Sometimes the 0 that you write is a 0 in R. Sometimes the 0 you write is a 0 in V. They're not the same thing. Okay, and we're going to do a whole sequence of computations where we're going from the left to the right. So let us start by minus lambda v. Okay, so now by part 6, we have that this is the same as multiplying lambda v here, just times minus 1. Yeah, this is what we've just shown. Yeah, so if it's true for v, it's true for lambda times v. Then we're going to use axiom 6 next. And in axiom 6, yeah, what do we have here? We have two scalars. We have lambda and we have minus 1. And axiom 6 tells you can first multiply the scalars times each other and then multiply the scalar multiplication times the vector. Okay. Now here we again inside R. So there we can use whatever we know about R. So this is now multiplication in R. So minus 1 times some lambda is equal to minus lambda v. So we got to the middle here. Now we want to get from the middle to the right. We're going to use multiplication R again. We're going to put the minus 1 on the right-hand side. So we have here, this is the same as lambda times minus 1 times v. Then we use axiom 6 the other way around, so that we get that this is lambda times minus 1v. And then as before, we're going to use part 6 to get that here the inside minus 1 times v is actually the same as the negative inverse of v. And we get to here. And so this is the end of the proof of this theorem and pretty much the end of this lecture. But before I let you go, I want to give you some summary of good things you want to do during writing a proof. So you should add that to your list of good proof writing. So what do we have here? We always want to explain the reader the ideas that we're using. We always want to reference the use of axioms or results clearly. Yeah, so every time you use an axiom, like here, axiom 6 in some equation, you want to tell the reader. Or if you're using a previous result that you've shown before, so in this case, I refers to some part, you could also refer to, let's say, theorem 1.2 or something like that. Or, you know, multiplication in R. Whatever you're using, you always want to reference what you're using. We see what it means that something is unique, and then we also see how to use such uniqueness. We reduce a proof to get more easily obtain some goals by using previously proven facts. So yeah, it's important to do that. The further along we get in this class, the more results we have at hand. And yeah, I mean, in every proof, you could reprove everything you've already proven, but this is very ineffective, inefficient, and also it will take you a long time. So it's very, the more results you have at hand, the more results you know, the faster you get to prove something and see connections. But be aware, only use results you've actually proven in this class. Don't go beyond that. Yeah, and so that is going to be it for this class.